we have the picture of the behavior of the function. I'm going to label my delta y out here and my delta x here, but this is a rectangle so that the delta y is back here and the delta x is here also. And we're going to say that all these angles are right angles, so that we have the point x naught, y naught, f of x naught, y naught here. And we have this rectangular solid, all of whose sides are equal to f of x naught, y naught. Now at this point, if we move in the y direction, we know that our function will at least start off in something like a straight line, provided delta y is small enough, and again provided the function is well enough behaved. And our delta x will give rise to a segment with a slope equal to the partial derivative with respect to x, so that slope fy of xy here, slope fx of xy here. Provided delta x and delta y are small enough, there's not going to be much curvature here, there's not going to be much curvature here. Although these lines are only an approximation, we don't expect to deviate from them by much. Also, if delta y is small, as we said before, there's not going to be much room for the fy to change a whole lot, so that we expect a side here to be parallel to this side, and I think I've kind of overdrawn that. Actually, I haven't. I drew that segment incorrectly. Okay, so I'm going to try to obliterate my mistake by some shading so that it's not as obvious. And we see that we have a flat surface here that's part of a plane. And we want to determine what the equation of that plane might be. Now we got slope fy here, fx here, and those are both evaluated at x naught, y naught, not at an arbitrary xy. And I'm going to claim that if we follow a line in this direction, in the direction of this slope segment here, that line is going to be part of a vector. If we carry that vector over here a y distance of 1, then this vector would be, well, 1 unit in the y direction is the j vector, so we go over here a distance equal to the length of the j vector, which is 1. And then what's the rise going to have to be? If you think about it a little bit, the rise over run of this triangle is the slope fy. So the slope of this vector is going to be fy, meaning if you move 1 unit in the j direction, you're going to have to move up fy times 1 unit, so that this vector is fy of x naught, y naught times k. Similarly, we could have a vector, if we move a unit distance in the x direction, then we will have moved along in the x direction along the I vector. In the y direction, we're going to have to have moved distance f sub x, or through a displacement f sub x. And that's going to give us the vector I plus fx of x naught, y naught, k. Now we're beginning to get a picture. We have a point here, and we have a vector in this direction that matches this slope segment, at least at the beginning, and a vector here that matches this sloping segment. These two vectors and this point define a plane. If I take the cross product of these two vectors, I get a vector normal to the plane. If I have the normal vector and a point, I can write the equation of a plane, so that I can find the equation of the plane represented by this red shaded region. So given a point x0, y0, 0 in the xy plane, we can find the point x0, y0, f of x0, y0. We can calculate the instantaneous derivatives in the y and x directions and use those to, first of all, construct a part of a plane that approximates the behavior of the function in this region, and also to get two vectors that define the orientation of the plane, so that what we have here is a plane through x0, y0, f of x0, y0, with normal vector, what? It's going to be j plus fy of x0, y0, k crossed with I plus fx of x0, y0, k. Cross product is not difficult to calculate because in this case we have only two non-zero components of each vector, so we can use the determinant definition or we can use the associative law. We could say this is j cross I. Well, j cross I, let's see, j is in the y direction, cross with I, that would be negative k. So that this vector, this normal vector, is first of all going to be negative k from the j cross I. Now, of course, we could have done this cross product in the opposite order and we would have gotten positive k, but just write them down in the order we thought of them. So j cross I is negative k. What's j cross k? Well, j direction, k direction. J cross k is the x direction, so that the j crossed with the fx k is going to be fx of x0, y0 times I. Now the fy times k crossed with the I, well, what's k cross I? K cross I gives us j. So we're going to have fy of x0, y0 times j. And what else? Well, we're going to have fx times k crossed with fy times k crossed with fx times k. K cross k is 0. This part of the cross product doesn't contribute anything. So we have a perfectly good normal vector, negative k plus fxi plus fyj, where fx and fy are both evaluated at our point x0, y0, because of course it's at that point that we calculated the instantaneous slopes.